here in 5.3, problem 4, we have a diagonalized matrix. So this is in the form, here's the matrix A, and here's an invertible matrix P, and then there's the matrix D, and here's the matrix P inverse. So this matrix is diagonalizable, and moreover, it's diagonalized. So the reason that we like diagonalized matrices, especially for things that we're going to do over and over again, if we want to calculate A squared, we can just take P times D times P inverse and square it. That's P times D times P inverse, and multiply it by P times D times P inverse. Now, matrix multiplication is not commutative, but matrix multiplication is associative. So this is going to be, what that means is I can remove the parentheses as long as I maintain the order. I can move the parentheses anywhere I want, but I have to maintain the order. And I'm going to group the P inverse and the P together in the middle. And now P inverse times P is just the identity. And D times I is just I. So this is going to be P times D times P inverse. So that's just P times D squared times P inverse. So the point of this, first of all, is to try to reinforce the idea that diagonalization is a useful factorization if it's available. And it's going to be especially useful in a problem where a matrix represents a change from one state to the next, and we want to examine that over time. So if A represents some iterative process, then I can, if we can diagonalize the matrix, it's much easier to compute a power of that matrix. And it goes back to what we know about matrix multiplication. Matrix multiplication is associative. Matrix multiplication is not commutative, so I can't change the order, but I can change the groupings. So for A to the K, we'll just end up with, so if I have A to the K, that's just going to be P times D to the K times P inverse. All the P inverses cancel out because they're in the middle. They all get rammed together. Another DVD bonus material, another thing that we should notice by looking at this construction is that A has eigenvalues of -3 and -2. So the eigenvalues of A are lambda equals -3 and lambda equals -2. Moreover, a basis for the eigenspace corresponding to lambda equals 3 must be 3, 2. And -2, -1 is a basis for the eigenspace corresponding to lambda equals -2. Got to remember what that means. That means if I take A and multiply it by one of these vectors, I should just get a multiple of that vector, specifically the eigenvalue times that vector. So let's test that out. A is the vector 1, 2, -6, -6. If I multiply that by the vector 3, 2, I get 1 times 3 is 3. 3 minus 12 is -9. And 2 times 3 is 6. 6 minus 12 is -6. And -9, -6 is -3 times what we started with. That's how eigenvectors work. Also, if you take 1, 2, -6, -6, and multiply it by the vector -2, -1, or any multiple of -2, -1, we get negative 2 minus 6 is negative, negative 2 plus 6 is 4, and negative 4 plus 6 is 2. We just ended up with negative 2 times negative 2, negative 1. Because that's how eigenvectors and eigenvalues work. If I take a multiple of negative 2, negative 1, say 1, 2, negative 6, and multiply it by, let's say, 20 and then 10. This is not an edit that needed to happen, but it was driving me crazy. It would have driven me crazy. So I get 20 minus 60 is, 20 minus 60 is negative 40. And 40 minus 60 is negative 20. I just get negative 2, the eigenvalue, times what we started with, 20, 10. I did it again. Half blue. Because that's how eigenvectors work. Any questions? Moreover, if I take 3, 2, and negative 2, negative 1 as a basis for R2, then the transformation x to ax will be diagonalized. As if we multiply by P inverse, that will turn standard coordinates into B coordinates. The matrix of the transformation will be diagonal, and then P will turn B coordinates back into standard coordinates. So much mileage out of diagonalizing a matrix. That's why I skipped over some stuff. Focus on the things that we get more mileage out of. So if I go from R2, here's R2, and I go to R2 over here, and the process is multiplication by A. And this is R2 in the standard basis. If I multiply by P inverse, that will go from the standard basis to the eigenbasis. It's still R2, but now instead of being under the standard basis, we're under the basis 3, 2, and negative 2, negative 1. I wonder why negative. That was strange. Now, to get to the codomain, that will be the process multiply by the matrix, the diagonal matrix D. And that will be R2. And that will still be images, B images. And then if we multiply by P, P is going to be the change of coordinates matrix from the B basis to the standard basis. So P inverse will be the change of coordinates matrix from the standard basis to the B basis. So in this case, multiplying by A is P inverse times D times P. We go from X to AX. And that's the same as P inverse times X, D times P inverse times X, and then up here, that'll be equal to P times D times P inverse times X. Get us to the same place. Any questions? It's a lot of mileage out of one problem. Once we know something's diagonalized, that's the usefulness of that diagonalized matrix. It could be that this process, multiplication by A, is some iterative process. Every year we go from this initial state to this final state, and we want to know what happens in the long run. So I want to know what happens as n goes to infinity, a to the n. What happens to a to the n as n goes to infinity? If I can get that down to diagonalized, then I just have to look at the powers of the diagonal entries, the powers of the eigenvalues. And that's a lot less computation than raising a to a power. It's too much computation in raising a to a power. Any questions? Comments? Snide remarks? How's everybody, okay? So if we remember, if B is a basis, let's say B1, BP is basis for vector space V, then the matrix made up of these vectors, B1, BP, is the change of coordinates matrix from B coordinates, oops, scroll up, to standard coordinates. That is, if I take this standard coordinates of x and multiply matrix B times the B coordinates of x, if I take the B coordinates of x and multiply by this matrix, I will get the standard coordinates of x. So these are standard coordinates. Here's our change of coordinates matrix, and here are B coordinates. If P is invertible, which is what we want for a diagonalized matrix, I can solve this equation for the coordinates of x relative to B by multiplying by P inverse on the left. And we can see that the P inverse changes from standard coordinates to B coordinates. So it goes the other direction. So that's why P inverse puts x back into the x into the B basis. Any questions? Any other diagonalization questions? All right, I'm going to pause the video here and we'll talk about next steps because we're running out of time for any more steps.